The AI system Fable has been credited with helping find a counterexample to the Jacobian conjecture. In other words, one concrete polynomial map that makes the conjecture's universal promise fail. We are going to build up exactly what that promise was and why this example breaks it. But first, here's the entire failure in miniature. 3 different inputs produce exactly the same output. Start with 3 inputs. Each one is just an address made from 3 numbers. The first is 0. 0, -1/4. The second is 1, -3/2, 13/2. And the third is -1, 3/2, 13/2. Whatever happens next, these are plainly 3 different starting points. Now send the first point through a polynomial map, a fixed rule built from sums and products of its input numbers. For this first input, the output is -1/4, 0, 0. Keep that output in place and send through the second input. It lands on the very same 3 numbers. Then send through the third. Again, the output is -1/4, 0, 0. 3 different starting points have collided at one destination. Now try to run the map backward. From that single output, should we return to the first input, the second, or the third? The output does not remember. This map is not one-to-one. Different inputs can produce the same result, so there is no single reverse rule for all of them. So far, this is simply a rule that merges 3 inputs. The surprising part appears only when we stop looking at the whole map and inspect one tiny neighborhood at a time. Stay close to input A, move it by one tiny amount, then another in different directions. Instead of asking where every possible input goes, ask a smaller question near this one point: does the machine keep neighboring inputs distinguishable? At this tiny scale, the map's derivative tells us how each possible nudge begins to move. Put those change rules into one table, and that table is the Jacobian, a local description of the map at this point. Now take the determinant of that table. Its job here is simple. Check whether those independent directions have been flattened together. If the determinant is 0, a tiny cell loses a dimension. If it is non-zero, the cell may stretch or shear, but it does not collapse. For this map, the determinant at input A is non-zero. That earns a precise promise. There are small neighborhoods around the input and its output, where the map has a unique reverse. Inside that window, each output leads back to exactly one nearby input. And input A is not special. This map's Jacobian determinant is non-zero at every finite input point. Move the little window anywhere, make it small enough, and the same local reverse is available. Now, zoom out. The reverse near A says nothing about the distant neighborhoods around B and C. Each neighborhood can be perfectly reversible on its own, even though their center points all reach the same output. The Jacobian tells us how to run one nearby branch backward. It does not choose a single branch for the whole map. That gap between nearby and everywhere is where the old conjecture placed its bet. Keep the local window and the global fork side by side. The proposed bridge between them was already built into this machine. Its coordinates are polynomial formulas fixed across the whole space. The bet was that this rigid algebra would force all those nearby reverses to fit together as one global reverse. That bet is the Jacobian conjecture. Take a polynomial map from a complex coordinate space back to itself. If its Jacobian determinant is the same non-zero number everywhere, then the map should have a polynomial inverse for the whole space, one reverse rule that sends each output back to its original input. The claim is older than the name usually attached to it. In 1884, Ludwig Kraus argued for the 2-coordinate version, but his final step was flawed. The proposed bridge had not been proved. In 1939, the statement appeared in work by Keller, and it later became conventionally associated with his paper. Kraus's earlier claim did not disappear. The same unresolved problem simply traveled under Keller's name. By 1998, Steve Smale placed the Jacobian conjecture as problem 16 on his list, Mathematical Problems for the Next Century. One reason he chose problems was the belief that a solution, partial progress, or even attempts would be important for mathematics. That is why one genuine counterexample would matter. It would overturn a universal claim selected for its mathematical importance. But a universal claim has one fragile word: every. The conjecture says every polynomial map that passes the constant Jacobian test must have a global polynomial inverse. One explicit map that passes the test and still merges distinct inputs is enough to break that word, and the opening map claims to do exactly that. Here is the whole suspect. Let U mean 1 plus xy and call the map F. Its three output coordinates are the formulas on screen. Nothing is hidden in U. Replace every U with 1 plus xy, and each output is an ordinary polynomial in x, y, and z. Now, both audit slots belong to one explicit object. First, the local test. Differentiate each output coordinate with respect to x, y, and z to rebuild the Jacobian table, then take its determinant. When those polynomial terms are collected exactly, every term containing a variable cancels, leaving Jacobian determinant of -2. -2 is non-zero and never changes, so the first audit slot passes everywhere. Now substitute the three opening inputs. At 0, 0, minus 1/4, U is 1. At each of the other 2 points, xy is -3/2, so U is -1/2. Carry those exact values through all three output formulas, and every row reduces to the same result, -1/4, 0, 0. The second audit slot passes too. Three distinct inputs really do collide. Why is that enough? Suppose F had one global inverse, call it G. Feeding the shared output into G would have to recover the input that produced it. But one input to G can have only one output, while this same point would have to return all three distinct inputs at once. So no global inverse exists. The first check satisfies the conjecture's hypothesis. The second makes its promised conclusion impossible. That is a complete counterexample. Start with the two inverse paths that ran into the edge of our window. The easiest explanation would be that they meet somewhere just beyond it. But suppose they met at any finite input point. Zoom in there because the Jacobian is non-zero. Some small neighborhood around that point has one unambiguous way back from nearby outputs. Two paths entering that same neighborhood would give two ways back from the same nearby output instead. So a merger at any finite point is exactly what the local test forbids. Now move the output point toward a perfectly ordinary finite target. One matching input does not have to settle toward a finite point at all. As the output closes in, that input can run farther and farther away. Enlarge the input window and it reappears near the new edge. Enlarge again and it has fled farther still. Its image stays bounded while the input grows without bound. This is a failure of properness. Infinity in the input can arrive at a finite output. Here is where that escape route hides in this map. Call the third output coordinate C. It factors as C equals x of 2 minus 3xy minus x squared z. Look only at outputs on the plane C equals 0. A product is 0 in one of two ways. Either x equals 0, giving a flat source plane, or x squared z equals 2 minus 3xy, giving a curved source surface. So the inputs mapping into this one output plane split into two geometrically different pieces. The flat piece gives one complete sheet of matching inputs. Each point of the target plane has exactly one match on x equals 0. The curved piece lies over that same plane twice. For a typical target point, it contributes two more matches, one on each curved sheet. So over this plane, the inverse picture is one flat sheet plus two curved sheets. Now follow the two curved matches as their x-coordinate approaches 0. Their surface equation can be written z equals 2 minus 3xy over x squared, and along these two paths z grows in size like 1 over x squared. The closer x gets to 0, the farther both inputs shoot away. They never land on the flat sheet at a finite point, even while their images approach an ordinary finite target on C equals 0. So the Jacobian test has not missed a local fold. It guards every finite neighborhood exactly as promised. What it cannot guard is an inverse sheet arriving from infinity. Keep one of those three inputs in view. Multiply its x minus coordinate by lambda, divide y by lambda, and divide z by lambda squared. The point moves, but two products do not. xy stays xy, and x squared z stays x squared z. Call them v and t. This balanced rescaling is the map's weighted scaling symmetry, and it reveals two combinations that can replace three separate coordinates in the inverse problem. Now fix one output target. Its coordinates determine two numbers, p and q. After the scaling compression, a possible input is encoded by one number, w, and that number must satisfy w squared minus w cubed equal to p times w minus q. The left side is the same cubic curve for every target. The target changes only the straight line on the right. So which inputs land here has become a simpler question. Where does this line meet this cubic? Suppose the line meets the cubic at three distinct roots, w1, w2, w3. The reconstruction rule turns each root into one pre-image of the chosen target. Color the roots. Carry those colors back through the rule, and the three inverse sheet colors from before return as three separate input points. For a typical target over the complex numbers, there are three distinct roots, and therefore three pre-images. This is what generically 3-to-1 means. Away from special boundary cases, one output has three inputs. Now, slide the target-dependent line to a boundary value. Two roots can become one repeated root in the compressed cubic. That might look like two finite inputs have collided, which the Jacobian test forbids. But reconstruction shows something else. The corresponding inverse branches run out to infinity. The repeated root belongs to the reduced equation. It is not a finite critical point of the original map. This is the algebraic shadow of the escape we just saw geometrically. Bring back the opening target, minus 1/400, and its three distinct inputs. They no longer look like a lucky numerical coincidence. They are one visible fiber of a map whose inverse problem is organized by a cubic. The forbidding three-variable formula was hiding a simple structure: one target, three roots, three preimages. Take our three colliding inputs and give each one the same fourth coordinate, say 7. Build a 4-coordinate machine that applies the old map to the first three coordinates and simply copies the fourth. The first three outputs were already identical, and the copied number is 7 every time. So three distinct 4-coordinate inputs now land on the same output, minus 1/4,007. The collision survives the extra coordinate. Now check the test. The new coordinate never mixes with the old 3. Changing it changes only itself at a rate of 1. So the new Jacobian has the old 3x3 block in one corner, a 1 in the new direction, and zeros between them. Its determinant is the old determinant times 1 to minus 2 times 1 equals -2. The 4-coordinate machine has both decisive facts, a non-zero constant Jacobian, and a collision. There was nothing special about adding just one copied coordinate. For any n3, let the first 3 coordinates pass through F and copy every remaining coordinate unchanged. Each copied direction adds another one to the Jacobian block, so the determinant stays -2. And if the 3 original inputs all receive the same extra coordinates, their outputs still collide. One 3-dimensional counterexample therefore gives a counterexample in every dimension n greater than equal to 3. But this construction only moves upward. It can add copied coordinates, it cannot remove the 3rd coordinate and turn this map into a 2-variable counterexample. That 2-variable problem, often called the plane case, remains open. So the exact verdict has 2 lines. The universal Jacobian conjecture is false, and it is false in every dimension n greater than equal to 3. The case n equals 2 is still standing. That fixes what the map proves. It does not yet tell us what can responsibly be claimed about how the map was found. Start with the public announcement itself. Levent Alpöge says Akhil raised the problem with him and that Fable worked on it with him during the World Cup final. Now set the question of credit aside and test the object itself. Exact symbolic arithmetic reproduces the original certificate. The determinant is always -2, and all three inputs land on -1400. A public lean development. A proof written so a small checker can verify each formal step, checks a rescaled version with determinant 1 and a collision between two distinct points. 2 points are already enough to rule out an inverse. The pull request was still open and unmerged when this archive was checked, so that status is not peer review. The algebra inside it is nevertheless available for machine checking. What we cannot audit is the route to the formula. No prompt conversation transcript, search history, compute record, conventional discovery paper, or measured division of labor has been made public. So the evidence does not support saying that Fable worked alone or assigning percentages of the discovery to model and humans. The strongest responsible claim is narrower. Fable materially participated in work that produced the counterexample, while Akhil and Alpöge also appear in the public account. How that collaboration actually unfolded remains unknown. Return to the 3 points where we began. They no longer look like a stray numerical coincidence. They are a tiny, exact witness to the whole global failure. A map can pass the local Jacobian test everywhere, carry 3 inverse sheets, let branches escape through infinity, and still send these 3 inputs to 1 output. That certificate settles the conjecture in every dimension n greater than equal to 3, whether or not we ever see the discovery conversation. The plain case remains open. So the final picture is deliberately uneven. The mathematics is compact and checkable, while the story of how Fable, Akhil, and Alpöge reached it is only partly known.